part 1 of lab 4. The first question asks us to develop a Moore state machine that will provide these sequences of signals under the control of 3 inputs. We have 3 inputs for this circuit here. One is EN, the enable stepping, and the conditions for that is 0 is the outputs. So 0, when it's 0, the output to the motor remains fixed. When it's 1, the outputs change. We have the clockwise input. So when it's 1, it's clockwise, and when it's 0, it's anti-clockwise. And the third input we have is from the clock module. This is going to control the rate of stepping of the motor. Here's the state diagram for the Moore's state diagram. So we have 4 states basically. We have S0, S1, S2, and S3. When the enable input is 0, it keeps on looping in the same state, in the state of S0, S0. And when clockwise and enable input both are 1, it changes from S0 to S1 and it goes clockwise. However, if clockwise is 0 and enable is 1, it goes anti-clockwise. As you can see here, it goes backwards. So for this state we have clockwise being 0, enable is 1, it goes backwards, it goes clockwise. Hence this is the same thing over here. We have the present state and the inputs. This is the enable input, this is the clockwise input. So when the enable input, and this is the present state is S0, so we're at S0 right now. Well, the enable input is 0 and the clockwise input is 0. The next state is going to be S0. So as you can see here, it stays in the same state forever. It keeps on looping in the same state. And when the enable input is 0, clockwise input is 1, it's still going to stay in the same state, S0. When the enable input is 1 and the clockwise input is 0, meaning it's going to be this state. So when the clockwise is 0 and enable input is 1, it goes anti-clockwise to state S3. And when enable is 1, clockwise is 1, this state right here, it goes to S1. And this is the same for S1, S2, and S3. And we got the JK inputs, outputs based on this table here, the flip-flop excitation table. And these outputs are based on the stepping sequence which we got from here. So S0 is 1 0 0 0 1 0 0 0. S1, let me just flip it over. Okay. S1 is 0 0 1 0. As you can see here, 0 0 1 0. S2 is 0 1 0 0. S2 is 0 1 0 0. S3 is 0 0 0 0 1, and S3 here is 0 0 1, and this state keeps on repeating over and over again. Okay. Let me show you the circuit, the sequence, the schematic for part 1. We're using a 748C107, which has 2 JK flip-flops. We're using a NAND gate, 2 NAND gates, and 1 XOR gate, combined with 4 AND gates, which all 4 of them are connected to the stepper module right here. So this is A0, B0. This is A0, B. This is A, B0, and this is AB. So these are the 2 equations which I basically used to form this schematic here, which I'll show you in a bit. So JA equals to KA equals to the enable input, and JB equals to KB, which is equals to EN into CW0 XOR A. So this where did I get this from? It's based on this we drew the K map here. As you can see here, O0 is A0 B0, O1 is A0 B, A0 B, O2 is AB0, O2 is AB0, and O3 is AB. So this is the schematic here. Let's move on to the actual circuit to see how it functions. Okay, so as you can see here, this is the enable input, and this is the clockwise input here. So as you can see, when both of them are 0, it keeps on looping in the same state S0. It keeps on looping there. And when enable is 1, as you can see here, let me change the frequency. Okay. As you can see here, when EN is 1, it keeps on looping in an anti-clockwise manner. And whenever clockwise is 1, it keeps on looping in a clockwise manner. And whenever you turn off clockwise, it goes back into anti-clockwise. And when clockwise is 1 and and enable is 0, you can see here it stays in the same state as well. So that's it for part 1. Thank you for watching.
My name is Robert and I'll be explaining part 2 of lab 4. So the question here asks us to create a 3-bit maximum length LFSR. And here we have the timing diagram for X0, X1 and X2. And the values for this we got from the truth table. And let me explain the truth table briefly here. So this is the present state and this is the next state here. And so from the diagram here, we can see that Q3 is equal to X2, Q2 is also equals to X1, and then Q1 is equals to X0. And this is the present state here, 1, 0, 0. And D3 is the XOR of Q2 and X1. So based on the truth table of XOR, 0, 0 gives us a 0 as well. And D2, as you can see here, is equal to Q3. And based on that, D2 is equals to Q3, which is 1 and 1. And D1 is equals to Q2. Q2 is 0, hence we have 0 there. And based on the D flip-flop truth table, the next state is the same as the D flip-flop. So hence the next state is the same. So 0, 1, 0 and 0, 1, 0. And the previous state is the same as the next state. As you can see here, 0, 1, 0 is the same as the previous state for this one, 0, 1, 0. And the same goes on for every other truth table. And as you can see here, we got this based on the timing diagram here. And the question asks us, what happens if the counter is in an initial state of 0, 0, 0? How can the second XOR help? It remains in the loop, and the XOR can be used to force a 1 to break this loop over here. Let's move on to the circuit. Okay, as you can see here, it's looping from 0, 0, 0 to 0, 0, 0 infinitely. And how do we break this? Is as you can see here, the second XOR is connected to ground here, and we can disconnect this and connect this to 1 to break out from the loop. As you can see here, it's looping. It's broken out of the loop, and this is 1, 0, 0, 1, 1, 0, 0, 1, 1, 1, 0, 1, 0, 1, 0, and it's going to keep on looping. And let's look at the oscilloscope here for XOR. Okay, so I'm going to change the frequency to 500 kilohertz. Okay. I'm going to stop the oscilloscope here. As you can see here, it goes to 0 and then 1 for one phase, 0 for one phase, and 1 for 3 phases, and then it goes back down to 0. As you can see here, this 0 is basically this phase over here, and then it goes up for one phase, and then goes down for one phase, and then goes up for 3 phases, and then goes back down for 0, and the loop still continues. And as you can see here, this is the exact same sequence we created. So hence, for this question, does the PBRS appear random? The answer is no. Part 2, the question asks us to move the 2 wires, and from the circuit schematic here, we changed from pin 4 and connected it to pin 6 over here, and from pin 5 to pin 12 as X0, as mentioned in the question here. And the question asks us if it's random or not. So from the oscilloscope over here, let me run and stop. As you can see here, whenever we stop the oscilloscope, the sequence is random. Thank you.
Part 3 of lab 4. My name is Ahmed. So basically, we have to design a milli-step machine to detect the sequence of 011. So milli-step machine, it's whereby the output is dependent on the input. So the for this diagram we just started with, whereby the initial state is idle. So the input, when the input is 0, it goes to the next state, which is F1, and when the input is also 1, it goes to the next state, which is F10. When the input is it's 1, it makes the output to become 1, so it goes to the idle state. And when the input is also 1, the output becomes 1, so it loops around within the idle state. The same thing is applicable to this one, which is when the input is 0, the output becomes 0, so it loops around F1. And for F10, it's quite different, because when the input is 0, the output becomes 0. It goes to the previous state, which is F1. So this is the state table for this one. It's just the same thing, which is we just drew the state table. So for the idle, when AB is 0, 0, when the input is 0, it goes to the next state, which is F1, and the next state at that particular the sequence is 0, 1, while the output is going to be 0. Since the output is 0, it goes to the next to next state. If it's 0, if at idle, when it's 0, 0, and the input is 1, it's going to loop around idle with the state of idle, which is this state, and the next state at that particular moment is 0, 0, so it becomes 0. The F1 when F1 is 0, 1, at that particular state it's 0, 1. When the input is 0, it keeps looping around the F1. When the input is 1, it moves to the next state, which is F10. So for that particular state, it's 0, 1, while the output is still 0. And when the input is 1, you can just see it goes F1, which is the same F10, it becomes 1, 0. So the output becomes 0. The F10, for the F10, when it is 0, it goes to F1. It goes to F1, which is F1, and the state for that particular moment it's 0, 1. And then when the state is F10, when the input is 1, it goes to the idle state, which is, it restarts, like it goes to the initial state, which is idle. In that particular state it's 0, 0, so the output becomes 1. So we drew we just use the same for the K-map. We just use those particular states. For DA, which is basically A, the D flip-flop, is basically B, W, and then for the B is actually a W node, and then F is actually a W. Okay, so we're going to move on to the schematic diagram. So DA is basically B node, BW, and then DB is the W node, and then F, which is the output, is AW. So the W by there is connected to the LFSR, and then we use this particular flip-flop HC74 for the D flip-flop, the AND gate HC08, and then the NAND gate HC00. The F and the W were connected to the oscilloscope. You can just see that. So this is basically F, which is the output, and then this is W, it is, you can say the input is this one. So when it is, you can see from the diagram, when it is 0, 1, 1, the output becomes 1. And then when it's 0, 1, 1, the output also becomes 1. So, and this one is because of the fake output. It's because of the fake output. Caused by the milli-state machine.